Better Buildings for Humans is powered by Advanced Glazings, makers of the Solera line of products. Solera is the leading glass glazing made specifically for architectural daylighting and with extreme insulation performance. Learn more at advancedglazings.com.
Hello and welcome to this week's episode of Better Buildings for Humans. I'm your host, Joe Menchefski, and this is the show where we look at the impact that the built environment has on our health, our wellness, our general well-being, our joy, and our productivity. And of course, I like to talk about sustainable design as well. And today I have somewhat of a legend in the world of mechanical engineering. You don't get to say legend and mechanical engineering in the same sentence very often, but today I get to do that. Today I have Peter Simmonds, an expert in mechanical design for very tall buildings. Peter, welcome to the show. It's an absolute pleasure to have you here.
Thank you. Thank you for having me. Hope I don't disappoint your introduction.
I'm sure this will be just great. Look, I always kick things off by having our listeners get to know our guests. Can you tell us about your career, the kind of work you've done, the kind of work you've been doing lately? And, you know, if there's any famous projects that you'd like to highlight, let's hear about it.
Oh, all right. So this is the BS part of it.
Absolutely.
I started, I left school. I wanted to become a professional footballer, and that never worked out. So I had to get a job. So I got a job as an apprentice plant fitter. And so I served my apprenticeship, and I carried on. We went to college, night school. So I finished really after about 7 years with a bachelor's degree in engineering. I got itchy feet, and I was lucky enough to go to the Netherlands by meeting someone who worked for a company. I worked for this company then called Van Hoogten, about 350 people designing hospitals. So the good thing about designing hospitals, unfortunately, it get very boring because you put the same project number on your week sheet for 2.5, 3 years, but there's nearly every item of mechanical engineering and building physics in a hospital. So it gives you a very good background. So I've done that. There's only so many hospitals that you can build. So then we started to move on to office buildings, and we started then playing around also with active beams and passive beams. And I'm talking then in the mid 80s, looking about that. Looking at the building physics, we soon worked out what condensation was. And that proved a plus later when we started introducing into the US radiant systems. So I was there. One of the other good things about it is we had a building physics department of about 12 people in with Van Hoogten. So it's very highly said. There's all these people. So when we started talking about glass, I mean, it was like being on a different planet. So we started looking at it, different types of glass, and what we're going to do with glass, look at mean radiant temperature in the space, you mentioned one of the things about doing glare. And I think that's the only thing that I haven't come across, only 1 or 2 papers, but no one has actually been able to define what glare is to the outside. I stay away from that. That's for the architect. But we just look at what the different types of glass are and what was possible. Let's see, I worked there until 94. And in 94, I sort of got romanced by Flack and Kurtz in New York office. And I went over there, worked first of all on contract work. We were doing a job in Shanghai for Helmut Jahn, the 21st century tower. And a good friend of mine always reminds me the best thing about that job was it never got built, because we think if it had got built, we'd have been sued from here to kingdom come. But anyhow, it was like one of the first days of actually doing high rise in China, which was an experience. So, back there, and different things. What I forgot to mention was one of my notable projects, Van Hoogten, was Groningen Museum. However you look at it, so the Dutchies are a bit crazy. So they decided to build this museum in the middle of a canal. So it's all surrounded by water and everything. But then you have a look at it there, and there were 4 or 5 different architects. So Kurtz, New York, I got there, and I got christened very quickly to go and start working on what was at the time KLCC, which is now Petronas towers. So working on those. They're only a mere 400 meters, but I mean, looking at things, and there were some things there that we learned about very, very quickly, and we had to repair very quickly because the normal chain of thought just wouldn't let us, or the physics, the chain of thought and physics didn't go hand in hand. There are different things that we had to revise, so we got that. What then happened, one of the first things I'd done there was a competition for the new Bangkok International Airport. It was SBIA as well at the time, as second Bangkok International Airport. It's now called Suvarnabhumi. So that was really good working on that. It was 550,000 square meters of radiant floor for cooling. So if you're going to do it, then we've done this. A fantastic project. It was good that we had a Japanese contractor, Joe, Japanese Thai contractors, because they were willing to go the extra one. If it had been Thai, poor people, they just wouldn't take the gamble. It was a gamble at the time because no one done radiant cooling at the time in Bangkok. So, but with the Japaners, we got that through. So one of the other things, and we used it as comfort by the gates and by the glass. So what we had there as a comfort criteria was 400 people, so waiting for a jumbo jet, waiting to board. And if you get there 2 hours before the plane goes, you're there for 2 hours. But if the plane for a technical gets there before it gets cancelled, you're there for another 2 hours. So the time was a 4-hour period of 400 people in there. And if people get a rate, their metabolic rate increases, so they produce more heat. If they look at the situation they were with the sun. So we looked at all these different things, and it was a good learning process, not only for us, but also for the other engineers of what happened there. So that was Bangkok. Then I moved to Hong Kong with Flack & Kurtz, worked on Chung Kong Center there and Chater Road and some other jobs. Not really big as it goes, but I mean, Chung Kong Center was 300 odd meters. Chater Road wasn't that high. It was only about 40 stories or something, but it was a nice project. Where do we go then? Oh, yeah. I joined a boutique company called IBE, Ideas for the Better Environment, in Sherman Oaks in California. So that was John Galtry and Alan Locke, both ex-Arab people, myself, ex-contract for Arab, so we knew what we were doing. And we joined this place. I was number 11 to join the company. So when we started working, one of the first projects we done was Water and Life Museum in Hemet. That's the world's first platinum museum. And it stuck right out there. And then basically what happened was it was supposed to be done down and dirty, rooftop package units, big volume spaces. And we knew that it wouldn't pass the energy because that was Title 24. So we had to come up with a low energy system. So out of the drawer came the radiant systems, and so radiant floor for heating and cooling there in Hemet. And that's how it manifested itself into a LEED Platinum. Another nice project for your company, it'll be interesting, looking at lots of glass and everything, was Akron Art Museum, which was what Wilfrich used to call the Cristal. And the design criteria for this, which is what the lobby was, but it was, if you've seen it, you can see how much glass it's got and what the orientation it's got. So there were two criteria for the lobby. One was in July, when there was a wedding reception in there, that it didn't melt the cake. And the other one was in January, when they have a fundraiser. So the men would be in tuxedos and the women would be in long dresses or whatever happened. And so you get there in a January night at 8 o'clock at night time. It gets pretty damn cold in Akron. So the idea then was to keep it comfortable. So that was the way we kept it within, the ISO 7730, or ASHRAE 55, PMV plus or minus 0.5. And that was the design criteria for that space. And with the radiant system, and the radiant system basically was a no-brainer, because if you look at the duct, the steel work and the Cristal, one thing that the Wolfbricks didn't want was this ductwork being routed around in the middle of the space and spoiled the place. So we've done that. I think Cooper Union was the next one up in New York. That was another radiant job that had also nearly everything in the radiant floors. There's actually 3 galleries in the basement area. There's also a big auditorium with a blanket displacement. The radiant ceiling panels, but then blanket displacement in there. And then in the offices and the classrooms had the radiant ceiling panels. That was also a LEED Platinum building in New York City. And the luck with that is by choosing to go with the radiant system, the amount of lowered ceiling space required was less. So we actually smuggled in 11 stories or 11 floors into the height of the building, because there's a height restriction in the middle of New York. Instead of 10, we got 11. So obviously the Cooper Union were very happy that they gained some more space. And I suppose the last one to sign off on that was a very interesting project, was the Louis Vuitton Museum in Paris, which is a Frank Gehry project. If ever you've seen any photographs or anything of that, even I have to admit, it's pretty impressive. So I guess that's my life up to now.
Do you want to bring lots of healthy, beautiful natural light in your building and still meet energy codes? Try Solera from Advanced Glazings. Learn more at advancedglazings.com.
That's your career up to now, for sure. That's amazing. Like, that's extraordinary. We have to talk about tall buildings, and we
Yeah.
have to talk about radiant heating and cooling. First, I want to talk very briefly about radiant heating and cooling, because you said a couple of things in your intro that I want to jump on. Where does radiant heating and cooling fall on the spectrum of efficiency? Like, everybody's focused on carbon these days. Everybody's focused on minimizing energy. On the spectrum of efficiency, where does it fall?
We got to get this right. It's high efficiency, low energy. I had a student working for me at IBE, and I got him to track because we were doing in California, we do Tidal 24, and then you've got ASHRAE 90.1. So we were doing all these energy models. So what we actually done is very simple. What engineer doesn't love a spreadsheet? We made a spreadsheet of putting everything in there of saying, how many percent lower than code was it and what was it done. So I've got all the ones on radiant, with the radiant, either radiant floors, radiant ceilings, or whatever different things, compared to what would be a conventional VAV. Appendix G of ASHRAE 90.1 says 40% glass and basically an overhead VAV system, basically. So that's your base case. A majority of the times we were far lower than what the base case energy was. And I mean, Cooper Union, I remember, because I was actually looking at numbers the weekend, that was 43% lower than code. Okay. Other ones are around 30%, 28%, 40% again. Now we're fast forward to where we are today in 2024. It's still the same energy. People are there. Yeah, we got global warming, but now everybody's fixated on this carbon, right? Now we went back even then, right back where the numbers started coming from with 2004. So you can use numbers, translation numbers in ASHRAE 189.1. So you can take a kilowatt hour of gas, a kilowatt hour of electricity, and you can look at what the equivalent, I'm going to say now, the equivalent CO2 emission is from that. Now you look at how many different tons. I'm not going to look at it now. I don't have it in front of me, but over the years of how much tons it was. And now I have to laugh at all these people in ASHRAE are running around like chickens with their head cut off. Oh, CO2 this, CO2 that, CO2. So the first question I always ask with CO2, what numbers do you have? And they have zero. They have no numbers. We're engineers. Let the numbers do the talking. If you want to cut back on CO2, you want to look at it instead of throwing it all out there. And nearly everybody quotes a Department of Energy report or something from 5, 6, or 10 years ago saying, buildings are consume, how much is it now? 60% of CO2 or whatever. Some ridiculous thing. And they keep using the same thing. If I see another paper from Energy in Buildings that starts off and say, the CO2 problem in the world is based upon 60%. So, but the point I'm trying to make very poorly now, because I don't want to hold your time, is it's up to each individual engineer and company if they want to make a CO2 statement, right? They can do. They're the designers. When you design a building, you look at a building, and I'm the first one to say as well, some buildings just don't go, about what CO2 is going to be. But a lot of times, if you sit down with people and you look at things and you go and you optimize your design, you're clever, you make it into a holistic design, you can reduce the CO2, which is the important thing. The thing that needs to happen is we've done a European Central Bank competition. I don't know how many years ago that was. And our energy was just based on CO2 reduction, because that's what people should have known. And we didn't win it, but, it was a good idea, a good way of looking at it. So I've probably bored you to death now, but, you asked about the energy side of it. We can cut down on energy, but it's CO2. And instead of waiting for everybody to do it, no, you can just start. You can do it on your own. Every engineer that might be listening to this or practicing it anywhere around the world, if they design a building, they can say, how can I make it more efficient? By making it more efficient, you reduce the carbon footprint of that thing. One thing I will repeat, and again, I apologize for taking up too much of your time. When you design buildings and when you look at these buildings, people forget that, first of all, there will be occupants in the building. And when we get onto the tall buildings, we talk about them. You have occupants, you have lighting, even though it's LED lighting, 4 watts a square meter or 0.4 watts a square foot. And just look at all the electrical equipment you've got in your office these days. How many chargers have you got? Look at your computers. Who works with one screen these days? Nobody. They all work with 2 screens. They've got everything. They've got their backups. They've got their iPads. They've got their phones, everything. Just look at that. So even if you don't take the external, like solar radiation or temperature, just look at how much energy there is in a building on a base building. And that's why when you look at all these people that win all these prizes, yeah, what is it? The Visitors Lodge at Yellowstone National Park, right? 2 or 3 people sitting around a desk, of course, is, insulated up to the hilt up there. And of course, that can be a net zero building with a thing, but it's not a commonplace building, right? You go to Toronto, you go to Chicago, you go to New York, you go to LA, and those are buildings that really that churn out. If they're run badly, their CO2 footprint is ridiculous. Have you fallen asleep yet?
Oh goodness, no! Yeah, like I'm asking these questions because I want to hear you talk, and I know our listeners want to hear you talk. So do not apologize. I love hearing the stories, and I love hearing the opinions too. I think that's it's a very, very important thing for the experts to weigh in on what's happening in the world today, in this particular world. So I love hearing you talk. Let's move to skyscrapers.
Yes.
To tall buildings. Trey has a definition, right? It's tall and mega tall.
There's tall, super tall, and mega tall.
Tall, super tall, and mega tall. What are those definitions, Peter?
Actually, the definitions were created by the Council for Tall Buildings and Urban Habitat.
Right.
So a tall building is 100 meters or taller.
Okay.
Super tall is 300 or taller, and mega tall is 600 or taller.
Okay.
Right?
Okay. Yeah,
and 600 is a fair old height. That's
pretty tall. There's no two ways about it. So what kind of challenges, let's talk about radiant heating and cooling. What kind of challenges are unique to these very tall structures?
Well, what really helps is in the overall efficiency. I mean, and it's absolutely nothing to do with a mechanical engineer, but it is when you look at it, and the architect. So when you look at a floor plan of a building, the idea of every floor plan is that the majority of the floor needs to be leasable. So whoever it is, the owner of the building or whatever, it can lease all that tenant out. Now, so let's go back. So in simple terms, a 600 meter tall building. So this is our building, right? We're doing 600. The top 200 meters this day and age are 5, 6, 7-star hotels. The middle 200 meters, high-end residential. And the bottom 200 meters is offices. In its rudimentary thing, I think any architect listening to this, they might laugh and do it, but then that's the way the buildings are split up to. So then, when you look at the hotel, you're going to need elevators and freight elevators to get from the ground floor or 01 or level 1 if you're American to go right to the top. So therefore, you need 2 risers. Then you're going to go to the office part of the building, but they're going to need anything up to 4 or 6 risers or whatever different things going up there. And when you get to the residential, and then you get to the offices, you've probably got the same. So if you can imagine your footprint then was some in the region of very easy 12, 16, sometimes 20 elevator banks. There's no room around the perimeter. So when you ask with that's the big question about tall buildings. So you don't want to complicate that with an all-air system where you've got to have fan room somewhere. Then you've got to start blowing your air around either up or down or sideways or floor by floor, whatever it is. So what happens is when you start looking at radiant, you can relax a lot of the constraints. You can improve the comfort of the people in there for heat and cooling because we know that we've got mean radiant temperature control, which is always better for comfort. And we can do that. And we can get away with a lower floor-to-floor height as well, should that be required. So instead of your standard 4.2 meters, you can get it down to about 3.8. So over 140 floors, that's a substantial height of the building. So that really is in a nutshell, very quickly. And, I mean, if you're in a 5, 6, 7-star hotel, they're only interested in one thing, is the site and phenomenous rooms. I mean, you look at the Shard in London now, that thing is sold out because it's a Mandarin Oriental hotel. Nearly every major building has a major hotel chain at the top of it. So, that's not what it's going to be. Residential, that's just your fixed income and that you're going to get some money in for it. The office is only because people want to go to a lucrative area. That's about it. But so that roughly is the challenge, making that fit, making that fit so it works, so it's maintainable. The other thing is that people forget this is that when you design one of those buildings, you've got a great team of people there, world experts on there, and then at the end of the day, they give the keys to a janitor to keep the building running. That's what you've got to look up for. Right. So does that answer your questions about tall buildings or not?
Very, yeah, very much so. We talked a little before we came on air, before we started recording, about glass. And Peter, I know you're not an expert in glass, but when I think skyscrapers, you mentioned the Shard, I think of all glass facades, right?
Yeah, yeah.
And specifically transparent glass. That impact on heating and cooling, is that you know is it the same for very tall structure, or is it more unique for a tall structure in terms of managing the solar heat gain, and also the thermal losses from, you're really only dealing with like an R3 for most of that glass, and that's center of glass.
The answer is, I have to express myself very carefully, but I will express it from myself as an engineer. It's the gain. So the gain being, if you take ASHRAE 90.1 as being energy, so without looking at it, so you can have your first sketches from your architect, which knows, okay, what the floor plate's going to be, and so you know what the facade's going to be, you know how tall it's going to be. ASHRAE 90.1 says the base case to which you're competing only has 40% glass in it. Well, you and I know, if you drive through any city in the world, there's a damn sight more than 40% glass in those spaces.
Absolutely.
So first of all, the challenge is to make the glass as proposed by the architect, and this is where we do support architects, because the architects come up with an idea and they're carrying all this, and they're looking into the future, and we're looking about what we've got there, and then so we got to play in between, or not be devil's advocate, but go in between and work out what we're going to do, and say, okay, this is the glass you've got, or the glass you can come now. I'm going to get chastised for this, mock architect to say, please read past page 1 of any documentation, because it's not going to be single clear glass you've got or anything. And you probably know more than I do. The database now for, international glass database of tested glass, this is another thing, when you go to Asia, you don't always get tested glass. I think it's about 3,500 different types, isn't there, of the glass? Something like that. So therefore, 3,500. The Windows 7 program from LBNL is absolutely fantastic. You plug and play and put it in there and make it. So if you've got your 40% glass and you've got your idea, so therefore you have a solar heat gain coefficient or shading coefficient, you know what your U factor is going to be, and that's your base case to which to not to compete with, but to beat. So you can get up there and beat it, because that's the biggest thing you do. Because in your let's call it a glass palace, if you like, because they've been called glass palaces and different things. You can actually show that your building is going to be emitting or not consuming X amount of energy more because of this glass to the outside or to the interior. That is the challenge, and that's what I call it, the game. The challenge, I suppose, is technically a better answer, and that's what you show. So when we do my report, you turn around and say, okay, this is base case, 40% glass, this is it, and this is where we are with your percentage of glass with this glass type and everything, and it makes it much simpler. Also, for decision making, because you're going to get then a contract or someone comes along, we can't afford that glass, and on our last building we only use this type of glass, etc., etc. Let's save so much money. And yeah, you can save money, but then you're taking one step forward and 5 backwards.
Yeah, that's my life every day, Peter. That's every day for me, for sure. Let's talk about passive heating and cooling. Have you ever worked on anything involving passive heating and cooling in tall structures?
Funny enough, yes. With Helmut Jahn, before he passed away, was involved in a building called Ice City, in mixed-use building in Moscow. It had 2 towers. They weren't super tall. One was at 240 meters, the other one was at 120 meters. And I've got to express myself very carefully now. So when you look at a lot of developers have like a Christmas list, a wish list of what they want, right? It's got to be energy efficient. It's got to have this. And we want natural ventilation. We want to cut down on the rest. People need to be able to address their windows and blah, blah, blah. So as it starts with there, so you say, okay, well, let's go in. So this building, we actually, working with Helmut Jahn, he made something really sexy in the facade that they could be manually opened windows. And so we made a whole natural ventilation that they can use it in. And believe it or not, Moscow's got a very strange temperature range. It's like plus 32, minus 32. I believe the biggest one in the world is Saskatoon. Canada is minus 40, plus 40, isn't it? So Winnipeg's pretty. You look at this and you say, so there are different ways, and actually using the ASHRAE adaptive standard 55 adaptive comfort, you can look at what the temperatures are, and you can provide a solution for natural ventilation. However, I don't know if you ever read about it, if you heard about it. There was that terrible fire in England many years ago, the Grenfell tire.
Yep.
Remember that, right? It wasn't
Yep.
high rise. It was what they said. Was it 20 stories, 30 stories?
It's an aluminum composite. Was that what it was? Aluminum composite cladding?
Well, that's where the finger's being pointed.
Okay.
It had operable windows. And you go and speak to any fire marshal, and anywhere is than anything like that is, as soon as you start playing around, and when you do it, you get backdraft, you get different things. And that was majority there because you can't control it. Because one of the nice things, if you do tall buildings, you get to learn about not the neutral plane level now, but the neutral pressure level, where it's going to be in the building, right? And a lot of work I've been doing with a Canadian, with Duncan Phillips now, of ex-RWD, is running all these different numbers and saying what's going to happen. And that neutral plane in some of the buildings we've been looking at was 600 meters actually. It will move 600 meters up or down the building depending upon what the temperature is going to be or the inside pressure. And the reason for the neutral plane is that if you have a fire signaled in a tall building, what they do is they put where the fire is being signaled into under pressure, so they just exhaust everything out, and the floor above goes into overpressure, and the floor below goes into overpressure. Well, what overpressures are we talking about? You have to maintain what that's going to be. No more rule of thumb. So that's the thing that comes in there. So it's a big fire and life safety talking point at present, what happens.
That's a huge issue. I can't believe I've never heard of that before. I mean, I've done a lot of interviews and have a lot of discussions about passive cooling and heating. And, obviously opening and closing the windows is a key component of that. It's a key component of air quality as well. I'm really shocked that the fire aspect of it just never comes up in any of the conversations I've had. That is a massive issue. I could do a whole show on that. I'm going to, actually.
Yeah. If you look at some places around the world, when you work in Hong Kong, for example, what they do is they have operable windows, which are operated closed. But if the fire marshal decides he needs to get smoke out of that space, he will open those windows on those floors. Right, the smoke will billow up to underneath the ceiling, and it will take the easiest way out. So it will roll it that way. But so that means you've got an operable windows, not window, but windows, very large areas on lots of floors. And that's what you have then. And where it gets really not scary, where you have to pay attention is when I described my tall building, I said that the middle section was residential.
Yeah.
So these people lay out how much, I saw that building you were talking about in Central Park. Someone said they sold one of the floors there, condos there, for $60 million. So you pay $60 million and some guy says, but you can't open your windows. Yeah.
Right.
Yeah, and it's scary, but the person above you or person below you says, I don't want you to open your windows because I don't want to be caught here in a fire. Right. Yeah, because the only way you can get out of the building is through it's going down. Just have a look at the fire truck. See if you can see a fire truck with a 600-meter ladder on the back. Yeah.
Manage the connection between building occupants and the outside world using Solera translucent glass. Learn more at advancedglazings.com.
Right. Yeah, really interesting. Oh my goodness, I can't believe that has never come up. That's extraordinary. All right, just because I want to cover, we could talk about this all day, but I want to cover a couple of other things. I want to talk about basically passive design or net zero design. Particular challenge in tall buildings because one of the greatest tools to getting to passive design is to put lots of solar panels on the roof, but you don't have much roof relative to total livable area in a tall building. Are there any other technologies that you can employ that helps you get closer to a net zero tall building?
Sure. Well, yes. I mean, unfortunately, the American and the Canadian view of it is everything goes on the roof. I don't care what the roof looks like, unless you go and work in Europe and everything. The first drawing the architect wants to see is, let me have a look at the roof plan. Get rid of that. So they want it all smooth. So anyhow, but you've got no room, as we discussed. You've got your satellite dishes there for all your IT work and what you're doing, especially if you've got trading floors in the building. And then you've got this massive glass wash installation to go to drop down 600 meters to clean the windows. So there's nothing there. You've got integrated PVs. Now, you work for a glass manufacturer. How many of those have you sold? You can look at them, they're on there, so they're not around there. So you've got to look elsewhere. Now, what you can do is you can set up PVs in arrays. You can cover the car parks, you can put other different areas or whatever. you've got to start looking at how much energy do you really need in the building and what you do with. When we done Louis Vuitton, we were lucky we had it on 2 aquifers. So basically, the chiller became a heat pump, and because it runs, that building is nearly net zero, including all the light and everything it's got in there, because it's getting everything out of these aquifers. So, but different places, I'm fully aware of where we are. Different places you just can't drill down. You don't have an aqua floating on your building. So what else do you want to do? It would help anything if you could get rid of all the mechanical systems or reduce their size, because it goes back to the efficiency of the building. Again, you've got something in there. But I mean, you can try, and then it's the maintenance. So you could do lots of adaptive cooling. But what do happen with the water about that? What happens if there's a drought? What happens if there's wind, etc.? So unfortunately, the big answer is to do self-generation, and then people look at that, and to at least manufacture your own electricity on site. I mean, how many of these buildings, when you look around, actually have their own emergency generators, or tenants have emergency? And what do? They run them, first Monday of every month, just to run it for an hour to see if they work. Why not run them full time and get the electricity back from this, and then put it into the building, and then do the heat reclaim? I mean, that's what we were doing in hospitals in the Netherlands 30, 40 years ago.
Right.
It's how you think about something, how you do it. But if the design team works on this and says, okay, we're going to design a 600-meter building with no major heating or cooling plant in the building, but well in the vicinity or in the ground, so we'll put our own energy plant on the corner. What you then do is if then get 4 people talking the same, or 16 people, and it says, okay, why don't we go back to a central distribution of steam in the old days, which is still there.
Yep.
Steam, electricity, and then just pump it around. I mean, Chicago's got a chilled water loop for downtown Chicago, made with thermal storage. So at nighttime they do low temperature, little things like that, and that's been around for 30 years. So it's there. It just sometimes the simple solution is there, but you just don't think about it.
Yeah, that's wonderful. And you also have to have coordination, and that's not a very North American thing. Each building is sort of their own little universe, and it's hard to think like the city. It's hard to think, in the larger urban perspective. So that's an interesting challenge for us on this side of the pond for sure. I want to talk. You mentioned the Council on Tall Buildings and Urban Habitats. You were involved with their design guide, and I think ASHRAE was involved as well. That was a joint effort.
Yes, it was primarily ASHRAE, and obviously we want to work there. And all the members of the ASHRAE team were members also of the CTBUH. So we just got CTBUH to endorse it. There's no point of having 2 entities talking about the same tall building in a different language.
Yeah.
So we went back and we done it for them. And we published another one a couple of years ago on stack effect, actually about a year ago. And that was just purely through the CTBUH.
Okay, well, that's what I was going to ask you. Like, that was 2015 when that guideline was originally published. Are there big changes that are necessary to make it current? Because I mean, like we talked about earlier, this focus on carbon these days, is that bringing any pressure to revise the guideline?
It won't be revised anymore because we revised it in 2020.
Okay.
We actually found out that between 2015 and 2020, there was I think there are about 12 essential items which changed in a 5-year period, and it was quite frightening when you do this. So though it won't be republished on that, there's nothing I've got going on the back of my mind that we can put in there to improve it. Every building is dynamic. See, there's only like a framework of what you can look at. It's really there for lots of people that haven't designed tall buildings or super tall, mega tall buildings, what you can look at and what you can do. I think we did run it through ASHRAE, through the technical committee on tall buildings, looking at the energy use index going around, who wanted to release them. Lots of companies won't want to release them, but in America, before I left the US, I believe there were 17 cities in the US that requested that, let's say, the developers or users or owners of tall buildings provided every year their gas and their electricity usage. So therefore, you could go back and deduce what the EUI was going to be. So it's around there. I don't know how many there are. It's my fault. I should have known, but it's there. So there's a responsibility of what these people are doing. So you can look at it. There are horror stories out there as well, but I don't want to do horror stories because there might be too many attorneys listening.
Right. Okay. All right. We're at that stage in the show where I'm going to ask the $1,000,000 question. Every episode I ask this question at the end, and I ask that our guests answer it from whatever perspective they would like. And that is, what makes a great building?
There's a very satirical answer for that. But what it is, it's really teamwork. Is when everybody understands what the other team player is doing and takes responsibility for it. That's what makes a great building, right? And you can look at it, what people do when they're in there, when they're doing things. The structural engineer is talking to the mechanical engineer and is talking to the architect. The architect understands what the mechanical engineer is trying to do. Electrical engineers, they're always a phenomenon, but you make sure that he pulls the cables in the right directions, and do everything. It is teamwork when they get there. If you have a building which is very often done, I'm going to add to this now, and I'm going to out a loop for 1 minute. You said I can't go on a rant. I will go on a rant. When people ask me, I've been lucky enough to work around the world. The cheapest place to work in the world with the cheapest thing is America, because they have this value engineered session. A couple of NBA guys getting in there. So this building's being built. It's running down the tracks. It's probably 70% finished. You're coming up to the items there, finishes in bathrooms and other bits and pieces. And they turn around and they say, hey, we can save you $200,000 or maybe, $500,000 or something like that. So at the time, we all know that construction costs, unfortunately, do run higher than the prognosis at the start of it, but it's all in there. So these guys, and what do? They take out the low-hanging fruit, controls, other bits and pieces, and do everything. So therefore, what it is, you bought a Lexus or a Mercedes or anything like that. What you're actually running around in now is a Volkswagen Rabbit, a Golf or something like that, not to be derogatory to them. What I'm trying to say is you haven't got the high things. And that's why it's very hard. So when you have a good team, I would be also prepared to say that everyone talks to each other and there's no value engineered sessions going on to take quality out of it. Because the money had to be in there to start off with, because it was a great idea. So we've got it in there, and then some guy comes on and says, it's like if you went and bought a car, and then you go and pick your brand new car up, and the guy says, yeah, where's the wheels? Oh, well, what we've actually done is we've saved you some money, but you won't get the money back. But what you will do is if you give us another $2,000, you can pick the wheels up next week.
Right.
Would that happen? The answer is no. So why do it to buildings?
Right. Oh, I agree entirely. Yeah, it's a bizarre process and another thing that I deal with every single day of my life, for sure. All right, Peter, before we go, do you have anything exciting that you're working on these days? Any announcements, anything you'd like to share? Promote?
I got a very exciting project, which is a barn for a symphonic piano player where they can give recitals and also do recordings in. It's just test your imagination. So that's something exciting.
That's very cool.
For me, I am getting paid for it, so it's doubly exciting. Yeah.
That's perfect. Yeah, that makes it even better. Is it a famous pianist, a famous keyboards player, or?
I don't know. My quote is that it's going to be there, and I know that they name and make of the piano, but it's just a challenge of bringing it all together where it's going to be.
Oh, okay.
I can't say anymore, but it's there. It's like, I do believe that this pianist has performed at Carnegie Hall. So there you go.
Very cool. Peter, thank you so much for your time. It's truly been an honor.
Thank you very much for having me as your guest.
All right. You take care. Oh, they will for sure. I'm quite confident. You take care.
All right. You too.
Bye-bye.
Bye. We hope you enjoyed this episode of Better Buildings for Humans. For more information on the world's best light diffusing and highly insulating glass glazing, please visit advancedglazings.com.